In today's lesson, we'll continue on big idea number 2. So how does bonding and intermolecular forces affect the properties of a substance? And work on this part of learning target number 5. So based on the structure of a compound, you can identify the intermolecular force it has and predict its properties. So what are intermolecular forces? They are electrostatic attractions between two or more molecules or ions. They were described by Johann van der Waals in 1873. There are 6 different kinds of attractions with different strengths depending on what two molecules you have next to each other. The strongest intermolecular force is known as an ion-dipole force. And when you make one of these, you get between 40 and 600 kilojoules of energy released, depending on which ion and which dipole you use. Definition is an attraction between the full charge of an ion and the opposite slight charge of a polar molecule. There's a couple of different ways you can do it. If you have a positive ion, you would have polar compounds with the slightly negative ends facing towards and forming an attraction. Or if you have a negative ion, your polar compounds would be flipped with the slightly positive ends attracted to the negative ion. Let's skip down to number 3, dipole-dipole forces. You get between 5 to 25 kilojoules of energy released. They occur between two polar molecules where the opposite slight charged ends attract each other. Now there's a couple of different ways that you can stack molecules. You can stack them linearly, where the slightly negative, slightly positive gets attracted and then continue on in a chain. Or you can attract them vertically, where you have them flipped orientation one above the other, or you can have some combination. Let's jump back to number 2, hydrogen bonding. It occurs when you've got two polar molecules as well, but it's a special case of dipole-dipole attraction. Whenever you have an H directly attached to an O, N, or F on one molecule, it attracts the lone pair on an O, N, or F on a neighboring molecule. The lone pair here is key to remember. Because OH, NH, and FH are the most polar bonds possible, these are not just slight charges, they are strong slight charges, which is kind of funny to say. You get between 10 and 40 kilojoules of energy released when these get made. In order for a hydrogen bond to happen, you must have two polar molecules. Some people get tricked by nonpolar compounds that have O, N's, and F's in them. Here's an example of a hydrogen bond. You have an H directly attached to an N on one compound, and it is attracted through a hydrogen bond to a lone pair on that oxygen, on the neighbor. There is an animation on hydrogen bonding. Make sure you check it out. Our next intermolecular force is known as an induced force. So number 4, ion-induced dipole forces. You get between 3 and 15 kilojoules of energy released. What happens when you bring something charged like an ion close to a non-polar molecule? It causes the electrons in the bonds of the non-polar molecule to displace or move. What this does is it causes the non-polar molecule to become temporarily charged or temporarily polar. Here's a diagram to explain. If I have a nonpolar compound here, I'll have equal distribution of electrons. If I bring a positive ion towards it, the electrons will be attracted to that positive ion, so they'll move to the side where the ion is, creating a slightly negative side and a slightly positive side to my nonpolar compound. Because I have opposite charges, they will get attracted together. Now, this is only temporary force. If this ion gets removed and is no longer near my nonpolar compound, then my nonpolar compound will revert back and the electrons will spread out evenly again. An example of this is the iron 2+ ion that's bound inside of a hemoglobin molecule in your red blood cells. How does hemoglobin carry oxygen? Well, oxygen is a nonpolar compound. Iron is an ion. Because it has a 2+ charge, the electrons in these bonds will wave in this direction. They will be attracted to the positive charge, which will create a temporary, slightly negative end and slightly positive end to my oxygen, creating a temporary polar compound. Now, you can induce charges with dipoles as well. That creates number 5, a dipole-induced dipole force, where you get 2 to 10 kilojoules of energy released. When you bring a polar molecule close to a nonpolar molecule, it causes the electrons to move in the nonpolar molecule. The nonpolar molecule then becomes temporary polar and will stick to the polar compound. An example of this is why oxygen dissolves in water. Remember, oxygen is a nonpolar compound, but it has to dissolve in water. If it didn't, then fish wouldn't be able to breathe. If I bring the slightly positive H close to my oxygen molecule, the electrons in this bond will wave and be attracted to that slightly positive H, which will create this O with a slightly negative, that O with a slightly positive, and those two compounds can be attracted to each other weakly. And finally, we have London dispersion forces. You get between 0.05 and 40 kilojoules of energy released when an LD force gets created. What happens is shared electrons, remember they're waves, so they constantly vibrate inside their bonds. This creates very small temporary charge imbalance. This temporary dipole then can induce dipoles in surrounding nonpolar compounds. So London dispersion forces increase with size and with surface area. Now, let's draw a diagram to show how this works. I'm going to represent a nonpolar molecule by drawing a bar. And let's say I have electrons in bonds all the way along here. Now, these electrons don't stay put. They like to move. So let's say this one waves a little bit this direction. That will set up a slightly negative portion to that bar where the electron's going to, and a slightly positive. That's temporary. Now, because that electron waved, this one is going to wave away. So is this one, so is this one, so is this one. And what this does is it sets up temporary, very slight positive and negative charges all the way down the molecule. Now, when this molecule is brought next to another one that has electrons in it, this electron here is repelled by the electron moving this way. So it waves in the opposite direction, setting up a slightly negative, slightly positive. And so then this one waves, and this one waves, and this one waves in this direction. And what it does is it sets up alternating slightly negative, slightly positive, all the way down the bar. Which then, those two bars get stuck to each other. Now these are only temporary slight charges. This electron here only waves this direction temporarily. When it waves back, then this will flip to being partly negative, which induce this electron to move back this way, flipping this to a slightly positive. So these temporary slight positives and negatives flip back and forth about 1,000,000 times a second, and they do it in synchronization, so that these two polar compounds will always have opposite slight charges next to each other, so they'll be attracted. Now these are very weak. Now, the way LDs work, the bigger your bar, the more electrons you have, which means the more they vibrate, which means the more slight charges you have, so the stronger the LDs. Same with surface area. Bigger surface area, more electrons waving next to that surface, the more slight charges that get generated, and the stronger the LD force is. So how do intermolecular forces affect the physical properties of a substance? Well, the stronger two molecules are attached to each other, the harder the substance is going to be, the higher the melting point, and the more likely it will be a solid at room temperature. Now, intermolecular forces are the primary influence on a molecular compound's physical properties. If you have an ionic compound, you have to break the ionic bonds in the crystal. If you have a metal, then you have to break the metallic bonds in the crystal. If you have a molecular compound, it's the intermolecular forces that must be broken when you're melting. Intermolecular forces can also be used to explain how a compound dissolves in water. The stronger the intermolecular force that can be made between the compound and water, the more it will dissolve. Now remember, when you are dealing with a molecular compound, you do not break the covalent bonds when a molecular compound is melted. It's just the intermolecular forces.